Another edition of Climate Chronicles. My name is Edward Rivero. My friends call me Eduardo, and we are in the month of May 2020, 16th of May 2020. On a Saturday here, I'm just going to present to you a little bit of the greenhouse effect, courtesy of Climate Reality Project. There's one issue that will define the contours of this century more dramatically than any other, and that is the urgent threat of a climate changing. From one of my favorite presidents, President Barack Obama, United Nations Climate Change Summit, September 23rd, 2014. One of the reasons I really like President Obama was because he prioritized clean air, clean water, and renewable energy. So I'm going to focus on that now, and then I'll disperse some of my comments throughout the article. Changes to the Earth and its atmosphere used to be measured in geological time. Millions of years to form canyons, ice ages lasting tens of thousands of years. We now live at a time when changes to the planet can be observed within one human lifetime, and sometimes within a span of just a few years. That's due to anthropogenic causes, human activities, especially carbon emissions from fossil fuel combustion. Starting about 150 years ago and escalating through the 20th and 21st centuries, these emissions have set in motion changes to our planet that may prove irreversible. Surface temperatures are rising, leading to melting of the ice caps and sea level rise. The oceans are becoming warmer and more acidic, killing coral reefs and affecting marine life. The first 16 years of the 21st century rank among the 17 warmest years on record. More extreme weather events, hurricanes, cyclones, flooding, heat waves, and droughts are making communities inhospitable and forcing people from their homes. Climate change is even affecting human health, with impacts on the air we breathe, our access to clean water, our ability to grow nutritious food, and our vulnerability to infectious disease from an expanding range for virus-carrying mosquitoes. Over the past half century, the average surface temperature of the Earth has increased by 1 degree Celsius, or 1.8 degrees Fahrenheit. This period is now the warmest in the history of modern civilization, and the warming trend is expected to continue. A recent assessment from the U.S. Global Change Research Program concluded that, based on extensive evidence, it is extremely likely that human activity, especially emissions of greenhouse gases, are the dominant cause of the observed warming since the mid-20th century. In addition to warming temperatures, the assessment describes the other human-induced climate changes that have been documented by thousands of studies, including melting glaciers, diminishing snow cover, shrinking sea ice, rising sea levels, ocean acidification, and increasing atmospheric water vapor. The greenhouse effect. To comprehend why the Earth's climate is changing, it is important to understand the greenhouse effect that regulates the climate in the first place. The Earth's atmosphere is a complicated system of gases and energy. It allows energy from the sun to pass through the Earth and also allows energy from the Earth to escape into space. By delicately balancing this exchange of energy, the atmosphere regulates our climate. The burning of oil, coal, and natural gas has increased the concentration of certain gases in our atmosphere. These gases act like a blanket, trapping Earth's heat and preventing it from passing through to space. This energy exchange imbalance grows as the Earth's atmosphere traps increasingly more energy that it can release and causes the planet to warm. The process works much the way a greenhouse would, hence the gases that allow sunlight to enter the atmosphere freely and trap heat energy in the atmosphere are called greenhouse gases. And ozone, or GHGs. These include carbon dioxide, CO2, methane, CH4, nitrous oxide, N2O, hydrofluorocarbons, and ozone. Fossil fuel combustion, coal mining, wastewater treatment, agricultural activities, and natural gas and petroleum systems are all examples of human-influenced GHG emission sources. So in that last part, just to reiterate, that the process works much the way a greenhouse would. Hence, the gases that allow sunlight to enter the atmosphere freely and trap heat energy in the atmosphere are called greenhouse gases. That's GHGs. And these include carbon dioxide, methane, nitrous oxide, chlorofluorocarbons, and ozone. Turning up the heat. Okay. Trying to get this to fit in the screen so you can see it. Okay, this is our world in data. Again, courtesy of Climate Reality Project of Orange County. Turning up the heat. For tens of thousands of years, the level of oxygen, nitrogen, and other gases in the Earth's atmosphere remained essentially unchanged. By the beginning of the 1800s, the world's population had grown to 1 billion, and the Industrial Revolution in North America and Europe began to clear the land and foul the air with factory smoke. A century later, the population had doubled to 2 billion, and the age of petroleum was dawning. After World War II, energy use skyrocketed. Between 1946 and 1968, the use of motor fuel doubled. Electricity consumption nearly tripled, and the production of petroleum-based plastics increased tenfold. From 1970 to 2014 alone, there was a 90% increase in the amount of greenhouse gases emitted into the atmosphere, with emissions from fossil fuel combustion and industrial processes contributing over 3/4 of the total increase. Agricultural deforestation and other land use changes have been the second largest contributors. Oil, coal, and natural gas power our automobiles, heat our homes, provide electricity for our appliances, and allow us to enjoy an unprecedented standard of living. However, when burned, combusted, these carbon-based fossil fuels combine with oxygen to form carbon dioxide. In the United States, carbon dioxide formed by the burning of fossil fuels makes up 82% of greenhouse gases. As a result of increased industrialization and combustion of these fuels, more and more carbon has been emitted into the atmosphere. The concentration of carbon dioxide in the atmosphere has increased by 40% since the mid-19th century. Carbon dioxide levels are now at their highest point in at least 800,000 years. The levels of carbon emissions grew sixfold from 1950 to 2014, when nearly 10 billion tons of carbon were emitted. Trees and other photosynthetic organisms take in carbon dioxide, but they can only absorb about 3 to 4 billion tons worldwide. As deforestation continues, the Earth will be able to absorb less and less. The United States emits more tons of carbon per capita than any other country. In 2014, the U.S., though containing just 5% of the world's population, was responsible for producing 15% of the world's carbon emissions. China is now the world's largest carbon emitter. But even with its rapid increases, China's carbon emissions per capita are still less than half of those of the United States. As industrialization escalates in Asia, Africa, and Latin America, carbon emissions in the developing world are increasing rapidly too. Other gases. Again, this is from Our Changing Climate, courtesy of Climate Reality Project. Other gases. Human activity is also directly related to the production of methane, another greenhouse gas. Methane is released by natural gas leaks, coal mining, oil and gas drilling, the burning of wood and garbage, the decomposition of organic matter, such as rice paddies, and digestion in some animal intestines. The atmospheric concentration of methane has increased 250% in the last 250 years, and currently accounts for about 16% of all global warming due to greenhouse gases. Worldwide production of methane is expected to increase as more cattle are raised and more rice is cultivated to feed increasing numbers of people. Although methane accounts for a smaller part of the greenhouse gas volume than does carbon dioxide, it is more potent. Each methane molecule is 30 to 40 times more efficient at trapping heat than a carbon dioxide molecule. Like carbon dioxide, methane concentrations have far exceeded the natural amounts of the last 800,000 years and remain in the atmosphere for years after they are emitted. Nitrous oxide is also known as laughing gas, is a byproduct of the fossil fuel combustion, bacterial reactions in soil, and the breakdown of widely used fertilizers. Its atmospheric concentration has increased 18% over pre-industrial levels, and it accounts for about 6% of the total warming due to greenhouse gases. Ozone-depleting substances, such as chlorofluorocarbons and hydrofluorocarbons, are completely human-made chemicals, unlike carbon dioxide, methane, and nitrous oxide. One chlorofluorocarbon, commercially known as Freon, is used as a refrigerator and air conditioner coolant, as a chemical cleaner, and in the manufacturing in foams and some aerosol sprays. Although chlorofluorocarbons make up a small portion of the total atmospheric warming, they are the strong insulators of all greenhouse gases. They are 10,000 to 20,000 times more effective at trapping heat than carbon dioxide and can live in the atmosphere for up to 100 years. Ozone-depleting substances deplete the ozone in the upper atmosphere, which carries its own set of severe consequences. The decrease of ozone lets in more of the sun's harmful ultraviolet light, which is known to cause skin cancer and eye disease, to damage crops, and to destroy the phytoplankton that support the marine food chain. In 1985, scientists discovered an ozone hole the size of the U.S. over Antarctica. This discovery prompted an international agreement, the Montreal Protocol, which was signed in 1987 by 25 participating countries in an effort to stop the production of ozone-depleting substances. Since then, 197 countries have agreed to dramatically phase out the production of ozone-depleting substances, and having successfully done so, the levels of ozone-depleting substances in the atmosphere has declined. Trends point to an increasing energy consumption in the future, particularly in the developing world, where the population is expected to grow the most. Globally, economic and population growth continue to be the most significant drivers of increase in carbon dioxide emissions from fossil fuel combustion. Both of these drivers are currently outpacing emissions reductions from improvements in energy intensity. Measuring climate change. Some question whether climate change is really happening, and if so, whether it's a human-caused phenomenon. On both counts, the science is clear. How do we know the Earth is warming? Evidence for a warming world comes from multiple independent climate indicators, from high up in the atmosphere to the depths of the ocean. They include changes in surface, atmospheric and oceanic temperatures, glaciers, snow cover, ice, sea level, and atmospheric water vapor. Scientists from all over the world have independently verified this evidence many times. That the world has warmed since the 1800s is unequivocal. How do we know carbon dioxide in the atmosphere has increased? High precision measurements of atmospheric CO2 have been taken from dozens of sites around the globe over more than 60 years. The instruments have been calibrated according to rigorous, internationally agreed protocols and have produced consistent readings confirming increasing carbon dioxide levels. Tiny air bubbles in Antarctica ice core reveal a historic record of atmospheric greenhouse gas concentrations, in particular carbon dioxide, nitrous oxide, and carbon CH4. Methane. I'm going to make sure I read that chemical property correctly. And chlorofluorocarbons. And, strike that. These bubbles, no chlorofluorocarbons mentioned in that part. These bubbles were captured in the ice as new, so let me read that sentence again, just so we're clear. Tiny air bubbles in Antarctic ice core reveal a historic record of atmospheric greenhouse gas concentrations, in particular carbon dioxide, methane, and nitrous oxide. These bubbles were captured in the ice as new snow accumulated at the surface and solidified into ice over the past 740,000 years. These records provide proof that through ice ages and warm periods, atmospheric carbon dioxide varied between 180 and 280 parts per million, demonstrating that today's carbon dioxide concentration of over 400 parts per million exceeds the natural variability seen in hundreds of thousands of years. How do we know that these changes are human-caused rather than naturally occurring? For more than 10,000 years prior to the Industrial Revolution, atmospheric carbon dioxide levels were essentially constant, showing that the recent increase in carbon dioxide is not naturally occurring. In fact, the increase in carbon dioxide has closely mirrored the increase in fossil fuel burning over the past 60 years. Scientists have used radioactivity to distinguish industrial emissions from natural emissions, showing that extra carbon dioxide is coming from human activity. Impacts on people and the planet. A difference of nearly 2 degrees Fahrenheit might not sound like much, but small differences in average temperature make a huge difference in the Earth's climate, affecting human communities and habitats for all species. Ocean acidification. Oceans absorb carbon dioxide like a mop. This helps remove some carbon dioxide from the atmosphere, but the increased levels in the ocean make the water more acidic. Since the beginning of the Industrial Era, oceanic uptake of carbon dioxide has resulted in acidification of the ocean. According to the Intergovernmental Panel on Climate Change, the pH of the ocean surface water has increased by 1/10, corresponding to a 26% increase in acidity. This acidity, combined with warming temperatures, is killing coral reefs around the globe. Species loss. Many species face an increased risk of extinction due to climate change. Most plant species cannot naturally shift their geographical ranges sufficiently fast to keep up with the current and projected rates of climate change in most landscapes. Sea level rise. Warming temperatures are causing land-based ice, such as glaciers and ice sheets, to melt. That, along with thermal expansion, water expands as it warms, is raising sea levels around the globe. In 2014, global sea level was 2 6/10 inches above the 1993 average. Sea levels continue to rise at a rate of about 1/8 of an inch per year. Sea level is expected to rise by at least several inches in the next 15 years and by 1 to 4 feet by 2100. As much of a rise of as much as 8 feet by 2100 can't be ruled out. Higher sea level means that deadly and destructive storm surge push farther inland than they once did, which also means more frequent flooding. Effects on agriculture. Reusable container. Reduce, reuse, recycle, refuse, and rot. The 5 R's. Effects on agriculture. Droughts and extreme weather events in tropical and temperate regions are expected to negatively affect food production, especially for the main grain crops, wheat, rice, and maize. Effects on fisheries. Warmer and more acidic waters will change the distribution of global marine species and reduce marine biodiversity, affecting the supply and variety of fish species. Effects on communities and infrastructure. Greater frequency of extreme weather events and flooding will continue to threaten the viability of many communities. In addition to storm surges affecting coastal communities, inland communities can also be vulnerable to climate-related events, including wildfires, landslides, and droughts. Earlier spring melt and reduced snowpack in mountain regions will affect the availability of water resources in the region. With some regions becoming inhospitable, people will be forced to move to other areas, growing the ranks of environmental refugees. Threats to public health. Extreme weather events are already taking a toll on human health. Since 1990, they have claimed 500,000 lives. The number of vulnerable people exposed to heat waves climbed by 125 million from 2000 to 2016. Warming temperatures have also expanded the regions for mosquitoes, which carry viruses such as malaria, dengue fever, and Zika. Public health will also be affected by climate change's threat to food security and clean water availability. Climate change inequities. Climate change is a global phenomenon. Even so, some communities will be affected more severely than others from the impacts of warming planet. Surviving changes to our climate requires adaptability, and that takes financial resources. Engineering projects like seawalls and levees to hold back rising sea level, public health capacity, emergency preparedness, and relocating displaced people all require significant financial investments. In less developed countries, these investments may not be possible. Subsistence farmers in less developed countries will be at the mercy of changing agricultural outputs from more droughts and storm surges. In addition to more food insecurity, vulnerable populations will also see threats to their livelihood, access to energy, water, and safe shelters. In short, less developed countries, home to most of the world's populations, are less able to cope with the impacts of climate change. A carbon budget. The consensus among climate scientists is that the continued emission of greenhouse gases will cause further warming and long-lasting changes in all components of the climate system, increasing the likelihood of severe, pervasive, and irreversible impacts for people and ecosystems. Without additional steps to curb greenhouse gas emissions beyond what's in place today, emissions are expected to grow, driven by increases in global population, a likely 50% increase by 2100, and economic activities. Baseline scenarios, those with efforts to mitigate greenhouse gas emissions, result in global mean surface temperature increases of 3 and 7/10 degrees Celsius to 4 and 8/10 degrees Celsius by the end of the century, compared to pre-industrial levels. Yet climate scientists warn that a global temperature rise of more than 2 degrees Celsius would result in dangerous consequences, including destabilization of the polar ice caps, devastating weather events, sea level rise, and agricultural losses. In the 2013 budget, the Intergovernmental Panel on Climate Change released a groundbreaking report asserting that as a global society, we must adhere to a carbon budget if we want at least a 66% chance of staying below the 2 degrees Celsius target. According to the IPCC calculations, this budget allows for 1 trillion tons of carbon dioxide to be emitted into the atmosphere from the industrial era on. The calculations begin in the industrial era to account for the fact that carbon dioxide remains stored in the atmosphere for centuries after it is emitted. We've already churned through more than half of the budget. At the rate we are going, we would reach the trillionth ton in 2040. Scientists have stressed that if we want to stay within our budget, carbon use will have to peak in 2020 and then begin to decline. In order for the global temperature to not rise more than 2 degrees Celsius from pre-industrial levels, carbon dioxide concentration couldn't rise above 450 parts per million by 2100. Achieving this would involve substantial cuts in anthropogenic greenhouse gas emissions by mid-century through large-scale changes in energy systems and land use. Let me read that again. Achieving this would involve substantial cuts in anthropogenic greenhouse gas emissions by mid-century through large-scale changes in energy systems and land use. We'd need to reduce our current emission levels by 40 to 70% by 2050 and get to near zero emissions by 2100. There are positive signs that emissions are falling in many countries as a result of regulations, but our transition to renewable energy must radically speed up to prevent the worst effects of climate change. The Paris Agreement. getting these efforts to accelerate and keep warming below the 2 degrees Celsius threshold motivated world leaders to work together and pledge to reduce their country's greenhouse gas emissions. In December 2015, these leaders met in Paris and reached a landmark deal, the Paris Agreement. The Paris Agreement is the latest step from the United Nations Framework Convention on Climate Change, an international treaty developed in 1992 to combat climate change. It follows the Kyoto Protocol, which committed developed countries to reduce their greenhouse gas emissions. The Paris Agreement brings all nations, developed and developing, together to combat climate change and adapt to its effects. It requires all parties to put forward their best efforts through nationally determined contributions and to strengthen these efforts in the years ahead. This includes requirements that all parties report regularly on their emissions and on the implementation efforts. As of November 2017, all countries have signed the agreement, including the United States. However, U.S. President Donald Trump announced that the U.S. would be pulling out of the agreement, calling it a, quote, bad deal, unquote, for his country. If the Trump administration follows through with its threat, the U.S. withdrawal would take effect in November 2020, right after our election. Before and during the Paris conference, countries submitted comprehensive national climate action plans. These are not yet enough to keep global warming below 2 degrees Celsius, but the agreement traces the way to achieving this target. The agreement is supposed to be reviewed every 5 years, but so that countries can ramp up their commitments. As part of the agreement, more developed countries are also supposed to assist less developed countries with financial and technical resources to adapt to a changing climate. Climate action plans include transitioning energy production and transportation away from fossil fuels. They also include plans for land use changes, such as afforestation, planting trees in barren land to create forests, which can help absorb carbon dioxide. Stabilizing population size and conserving resources are part of a long-term climate mitigation strategy. Universal education and equal roles for women in societies lead to smaller families, gradually reducing population growth. And here's the caption for this picture if you wanted to see that. Your carbon footprint. Okay. Annual global anthropogenic carbon dioxide emissions, gigatons of carbon dioxide equivalent per day, from fossil fuel combustion, cement production and flaring, and forestry and other land use, 1750 to 2011. Cumulative measures and their uncertainties are shown as bars and whiskers, respectively, on the right-hand side. As an individual, there are many efforts, small and large, that can reduce one's carbon footprint. Anything that reduces your daily energy use also keeps carbon out of the atmosphere. Around your home, this includes using energy-efficient appliances and lighting and adjusting the thermostat to use heating and air conditioning more conservatively. Our transportation choices directly impact our carbon footprint. Limiting car trips, using mass transportation, and taking fewer flights are just some ways we make a difference. Because food choices influence land use, you can reduce your carbon footprint by eating lower on the food chain. Livestock uses tremendous amounts of energy resources and emit methane, and wasting less food in general. Using cleaner technologies such as solar panels and electric cars also lessen our carbon footprint. The multiplication of carbon mitigation efforts by individuals, industries, and governments will be key to determining what kind of planet we will leave for future generations. The impacts of climate change are already observable, but the urgency of our response can make a difference on how much and how quickly our global climate changes and how we can help communities adapt to those changes. This is Eduardo Rivero, live from Downey, California. Thank you for your time.